Morning everyone. Nice to see so many people getting up bright and early, still coming to listen to me, so that's good. Okay, so the tail end of the last lecture we started looking at this model of a transistor which we called a large signal model, and it was made up of a current source, which was a dependent current source, and a diode in this part here, and we started looking at the transfer function of this transistor when we put it into a sort of a circuit. And we got the idea that actually this is a pretty good representation of a transistor across pretty much all operating conditions, but with that comes a bit of complexity. Even though we call it a simple large signal model, it's still quite complex because we have a diode in here, and diodes are exponential. So suddenly we don't have a linear system, we've got an exponential system. So it's quite accurate, but not easy to work with. So we said, could we actually try and simplify this a little bit? Because as engineers, we like to try and massage things into a shape that we can use them and apply a common set of rules. And having gone to all this trouble of learning about network theory and mesh analysis and other things and linearity, it'd be a shame to have to not be able to use it because the devices we want to use are non-linear. So we try to come up with an approximation of a linear system for a transistor that allows us to apply the linear theory that we've learnt and make life a bit easier for us. So it requires a little bit of knowledge, and as we go through the course you'll understand a little bit more about why this isn't such a bad idea. So what we're going to do is we're going to replace the exponential bit of our transistor, this diode down here, with something that's a lot more linear. And we've replaced it with a battery, or a voltage source, because it's not really a battery, just drawn as a battery. So a voltage source of about 0.6 of a volt or so, anywhere between about 0.5, 0.7 would probably do, and this thing called an ideal diode. And an ideal diode is a diode symbol with a square around it, and that just means it's got perfect transfer characteristic, which means that it's completely on for any voltage bigger than 0 across it, and completely off for any voltage less than 0 across it. So its transfer characteristic looks, let me draw a pen on here. So its transfer characteristic, I'm going to change colour otherwise you won't be able to see it. Will look like off down here, and then when it gets to 0 it goes on completely. So those two lines are on the same time. So it's any negative voltage applied to the diode, there's no current flowing, and any positive voltage applies to the diode, it suddenly has completely on. So this is basically either a piece of wire or an open circuit, depending on which way current is trying to go through it. Let's go back to red, like red. Okay, so that's an ideal diode. So that's what we've got here. So any current trying to flow in this direction, straight down, is going to flow through here like it's not there, and just see this 0.6 voltage source. And any current trying to go in the other direction can't, because this diode is saying I'm not letting anything pass, and it's ideal. So that's what we just accept. So this combination of a diode and a voltage source gives us this characteristic. Okay, so basically as soon as the voltage across this diode becomes bigger than 0, which means the voltage between this point base and the emitter here becomes bigger than 0.6 of a volt, because remember we've got 0.6 volt here, so it just needs to be bigger than 0.6, then this diode is on and anything can flow through here like this. So that's all we've done. So this 0.6 of a volt merely moves this vertical line either left or right. If it was less than 0.6 it would be down here, if it was more than 0.6 it would be up here. So that's all we've done. We've just given ourselves this very simple straight line transfer characteristic, which looks like that. And if we compare that with the real equation, or the real transfer characteristic for when we had a diode in our loop, the diode looks like an exponential. So what we're trying to do is we're trying to make this linear approximation look like this response here, and it only really looks like it in this bit here. It doesn't work down here, and it really doesn't work down here. So we've said this looks a bit like a straight line, and we'll model it as a straight line just to start with. That's all we've done. So there's always some limitations here, but you get the idea. And this works because we only ever operate this transistor in a region where it's on this part of the curve anyway. Let's say 90% of all operations with transistors will be somewhere on this curve, and will also be fixed about a small point on this curve, and we'll worry about that in a bit. But if we accept that, then really all we need to do is approximate this straight line at this point, and we don't really care what happens elsewhere. Okay, so that's just looking at it under a very narrow set of conditions. On the output side, we've got a current source, and we know a current source just gives us a constant current irrespective of the voltage across it for different values of IB, because the current source is controlled by IB. So whatever we change here gives us a bigger change in here. So that's why we have to have a family of curves. Okay, so these are just examples. There's a continuous set of curves between here. In this case, with this simple model here, the model actually is valid all the way down here, but the reality is that that's not what a transistor does, because a transistor obviously has this saturation region. So as long as we only operate in the active region of the transistor, this is actually a pretty good model as well. So what happens in here, it won't be true, but as long as we don't operate in that region, then it doesn't matter. Right, so that's where we got to. So as an example of how to use the simpler model, we can take a transistor circuit. So here's a typical transistor circuit. We've got a transistor, and we've got a resistance in here, and we've got a load resistance over here. So this is where dissipation occurs. And so to analyze this, we would replace the transistor with our transistor model, and in this case the simpler linearized model. So we've got our current source, our ideal diode, and our 0.6 for a volt. And remember, this isn't a real battery. You can't go digging in the transistor and trying to find it. It's not there. It's just an abstract representation of what the model looks like. Put our resistors in, put our sources in, and then we can start to see what's going on. And we can see that we're starting to see meshes, nodes, things appearing. So if we take a bit of an approach on this, we can start to apply some of the knowledge that we've done earlier. But this one is actually quite trivial in some ways, so we can do this by inspection, but we're implicitly applying Kirchhoff's rules and Ohm's law and things like that as we go along here. So we have to ask ourselves, what are we interested in? I've lost my little pointer. Where's it gone? There it is. We're interested in the output voltage, and the output voltage is defined as the voltage across this transistor. So we want to take the voltage at this point here, and that's this point on the circuit. So we are interested in this voltage in this mesh or loop. So with a bit of common sense and a bit of looking at this, we can actually say, well, actually this voltage here could be the sum of the voltages and things across here, but we've got a current source here, and we're never sure what the voltage actually is across a current source. It's not defined. But we are sure of what the voltage is across a resistor, because Ohm's law applies. So to find out what the voltage is at this point here, all we've got to do is work out the voltage drop across this resistor, because we know one end's at VCC, and that's not moving, and the other end is just Ohm's law. V equals I times R. So whatever the voltage drop is across here, we can subtract it from this one, and that gives us V out, and we don't need to worry too much about what's going on down here then. So we can formalize that and say that V out is equal to VCC, which is this voltage here, minus whatever is dropped across here, which is going to be whatever the current is through it, times RL. And the current, if we look at it, is right here, staring us in the face, is beta IB. That is the current going through here. So just by looking at this top bit of the circuit here, we can get enough information for what we want to know about it in principle. So we've got an equation for V out, which is what we're interested in, which is defined as VCC minus beta IB times RL, which is just the voltage drop across this resistor, and take that away from here. But we've still got IB. We don't know what that is. So we have a look at that, and we can see from looking down here that IB is just what's going on in this little loopy thing here. And so we look at the sources. We've got a 0.6 source. This diode, because current we're assuming is going through here, this diode has nothing across it. It's just like a piece of wire because it's ideal. And so we've really got Vs at one end of this resistor, 0.6 at the other end of the resistor, and a value of Rs, and that gives us a value of IB. Vs minus 0.6 over Rs. And remember, there's a caveat here, only for supply voltage or signal voltages that are bigger than 0.6 of a volt, because if this is less than 0.6 of a volt and we look at this loop here, then this is a bigger voltage than this, and it's going to try and drive current this way, and the ideal diode won't allow that, and so the current will be 0. So this only applies, this equation only applies for Vs bigger than 0.6 of a volt. Note that we're not actually interested in what happens for Vs less than 0.6 of a volt, because we're going to say that we're never going to allow that to happen. So it doesn't matter what happens then. Okay, so we've got an equation for V out. We've got another equation that's got V in. We're going to be interested in V out over V in, or the relationship between V out and V in. We've got this other variable IB, but we have a definition of IB, so we can make a substitution. So if we make the substitution for IB, for Vs minus 0.6 over Rs, we end up with this. So all we've done is put IB into here. Okay, so rearrange all that and we end up with this expression, VCC minus a whole bunch of stuff, Vs minus 0.6, which looks a bit more complicated than it really is. It's really just the equation of a straight line, because we've got V0 dependent on Vs. There's some coefficient applying to Vs, and that coefficient is a constant, and that also applies to this, makes another constant, so we can bring these all together. So you've got a big constant, that and that, and some relationship with Vs, which is the equation of a straight line, y equals mx plus c. So the gradient of this, which is the thing that we're going to be interested in, the rate of change of output voltage with input voltage, which you can write as a differential, but it's really just the gradient of the straight line, which is just this coefficient here, is equal to minus b over RL over Rs, and that's the gradient. Right. So if we plot that, we can see maybe how it's starting to help us. This bit over here, let me put this back as a pointer. There. So this bit over here is the real characteristic for the real device, if you like. And remember, it's got this exponential nature and its transfer characteristics. This is a relationship between input voltage and output voltage. So nothing much happens till about 0.6 of a volt, then it starts to turn on, and then it rises exponentially falls very exponentially very quickly. And then it can't go any lower than 0 in principle, but actually about 0.2, 0.3 of a volt in practice, and then goes flat like that. So this is the transition area, and it's the bit we're interested in for that circuit. Now the model that we've just looked at, the simplified model, is this bit. Yeah. All we've done is we've replaced it with a straight line. Now in reality this straight line really goes on up and down in the mathematical terms, but we also have to apply a little bit of common sense and say, well, we can't go any higher than VCC because that's the power supply, so it can't go any higher than that, so that obviously gets clipped at that point there. And we can't go any lower than 0, so wherever it crosses the 0 axis, that's where it goes, and we know it's never going to get quite to 0, so we just add a little bit, 0.2 of a volt in there. So that's equation of a straight line. That's the bit. The slopy bit is where our model actually applies. These bits at the end is where our model doesn't apply, and we've just applied a little bit of common sense to what happens in those kind of areas. So we can easily get voltage gain by a suitable choice of RL, RS and beta, because that controls the slope, and the slope controls the gain. Because if you think about a signal coming in here, and we'll look at this in a bit more detail later, a small signal coming in at this point here, so wobbling over a small region here, yeah, so it's varying between, in this case, should we say 0.8 and 0.9. Let's get the pen on it again. And this is where it's going to go very badly wrong. Okay, so let's say that we've, yeah, straight away, no straight lines. So that's our range of operation here, that's our signal coming in, and you can see that it's operating now across a much bigger region. So a small input variation here maps to a large variation in the output over here, and you can see that the slope of this line dictates how much of this variation we get. So if we make the slope really steep, we will get a very, very high gain in principle, a very high amplification factor. If we make the slope much more shallow, we will get less gain in terms of voltage in compared with voltage out. Right. Note we also have power gain. So you'll be going, oh, how do I note that there's power gain on this? And I also say it is very important because we've increased the power of something, which is obviously a good thing to do. And that's because we can define, there are different ways of defining power, but we can define the input power as VBE over IB in this case. So this is going in. So we've got IB going in, we've got VB across our input, if you like, and so power equals voltage times current, so that's VBE IB. And then output power, well, we say what's this thing doing that's useful? Well, it's putting a current through this resistor at the moment, and it's dissipating energy in this resistor. So if this resistor was something useful, say, I don't know, a loudspeaker or something, then that would be doing something very useful for us. And the power into that we know to be I squared C times RL, which is just V times I in another form. So the gain of the power is output power over input power, which is this kind of thing here, and that is equal to beta times IC RL VBE, when we say that IB equals beta, sorry, IC equals beta IB, and that is bigger than 1. Okay, because beta is a big number to start with, IC is a big number, RL can be as big as you like, and VB is quite small. So that gives us a power gain. So we've amplified a signal and given ourselves a power gain. So what have we learned in this so far? The large signal model we looked at is accurate but difficult to use by hand because it's got that diode in it, which is an exponential, and no one likes doing exponential calculations on a piece of paper. So we tried to simplify it. There's a simplified large signal model. It's easy to use, as we've seen, in terms of allowing us to apply linear theory, and so the maths becomes just simple algebra. But they will only be completely accurate at one particular point, because the straight line and the original curvy line will only ever cross at one point. That's just the nature of it. But they do allow circuits to be analysed using linear theory, such as mesh analysis, and as long as you don't move too far away from this one point, it's going to be pretty accurate. And both of these techniques allow us transfer functions to be developed. Right, so let's look at a different type of circuit. We have looked at just now, well, the last couple of lectures anyway, something called a common emitter circuit. We're now going to look at the common collector circuit in a little bit more detail. So this is a common collector circuit. Okay, the collector is this allegedly common, might not be completely obvious at the moment. So what we've done is we've moved this load resistor into this part of the circuit, whereas previously it was up here. So we've just swapped it over. Okay, and the previous circuit gave us some power gain and also gave us some voltage gain as well. So that was quite a useful little circuit, the one we just looked at. So let's analyze this and see what's going on. So we've got a simplified model. All we need to do is swap this transistor out, swap in our simplified model, and redraw our circuit. So here's our simplified model. We put this diode, this ideal diode, in there to remind us that there are some limits into when this thing can operate. We put our imaginary battery in there just for the abstraction purposes, the resistors and the current source. So this is our transistor model, which is it bit here. We just dropped it in and redrawn the circuit, and now you can see, I don't know what this is, but you can see that we've got a couple of meshes going on. So we can look at that if we want to as well, using formal mesh analysis, but it's quite simple. And again, take a note of where V out is on this circuit. V out is being taken across this load resistor again, but the load resistor has now moved. Okay, so on our circuit, this is where V out is, so that's what we're really interested in. If we're going to do the relationship between V out and V in, we need to know where V out and V in are on the circuits. So this is where V out is, and this is where V in is. So we can apply around our loop IBRS, the voltage across here, nothing going on over here, assuming that Vs is big enough. 0.6, which is that 0.6 over voltage we come across here, and then we've got whatever's going on through here, and this is the interesting bit, we've got IB 1 plus beta RL, because we've got 1 plus beta coming down here, and we've got we've got beta IB coming down here, and we've got another IB coming down here. So here we've got IB plus beta IB current going through here, multiply that by RL. And then that's telling us what's going on. We don't need to go much further than that because we've got enough information now to get V naught out. V naught is equal to 1 plus beta IB, which is just the current through this resistor, multiplied by RL, which is the value of that resistance. And now we've got the same as before. We've got two equations. We've got an IB in both, and we can make a substitute. We can rearrange to get an IB, make a substitution, and that will give us a relationship between Vs and V out. So if you want the detail of that, we just rearrange this to get IB as the subject of it, and if you do that, IB becomes Vs minus 0.6, so we've moved our 0.6 over here, and then we'll divide through with what's left to give us Rs plus RL 1 plus beta, so that's our value of IB. Substitute that for IB in here, and it gives us this, which is starting to look a bit complicated, but notice that this is just the equation of a straight line. We've got some coefficient of Vs if we multiply this out, and then some constant factor, so that's all we've got there. If we want to get the gradient of this, we can either get it into the form of y equals mx plus c and pull out the m, or we can just say we'll differentiate it and get the slope. And if we differentiate it, it becomes very straightforward, and we're just looking at the coefficient of Vs, which is just this bit over this bit. So 1 plus beta RL over Rs plus 1 plus beta RL, which on the face of it looks quite complicated. In practice, you can make this to be very, very close to 1, because remember beta is a big number, and let's say that RL is similar in size to Rs as a starting point. It might not be, but let's just say that. So 1 plus beta is a big number. A big number times this is going to be a really big number, and it's going to be much bigger than this number. So this bit is the dominant part of this equation, and if we want to make an approximation to it, we can ignore that bit, because this is 100, 200, 300, 400 times bigger than this. And if we do that, we've then got 1 plus beta RL over 1 plus beta RL, and that's 1. So all this nastiness boils down to approximately 1. It's always going to be less than 1, but not much if we can arrange for that approximation to be true. And if that's the case, then the relationship simplifies down to V out is approximately equal to V in minus 0.6. So that's a much simpler approximation than this lot over here. Okay, so we can make these applications only if this is much bigger than this. Right, so what that's telling us then is the output voltage, which we take here for example, just follows the input voltage of the same size, so there's no amplification of voltage as such, and in fact it's just 0.6 volt times shifted downwards. Output voltage equals the input voltage minus 0.6, so it's just 0.6 volt lower. Scale's the same, it's just been offset. Okay, so we haven't really amplified anything, and if anything we've just shifted it downwards a bit, which is maybe not such what we want. But there are some other advantages to this circuit. So if we take our circuit with our load resistor in here, and we pretend when we look in, so we're doing an imaginary look into the circuit. If we were a signal looking in here, what will we see? And what we're trying to do is come up with the Thevenin equivalent of this bit of the circuit looking into the transistor and the source. Right, so we're starting to get a little bit more abstract now. So we can look at that and say, well, okay, if we want to treat that as a black box and turn it into Thevenin, we need open circuit voltage and we need short circuit current. That's one way of doing it. Question. Is 0.6 okay? Yes, it depends on the transistor and how hard you're driving it on. It's to do with the point at which we tell ourselves that a transistor is turned on. So it's how much on are we operating up, and depending on the transistor and how hard you're driving it, it can be anywhere between about 0.5 and 0.7 of a volt. So 0.6 is a good starting point. It turns out to be not that important exactly what it is for most applications, so we just approximate it to 0.6. And I'll explain why it's not important as we go forward a bit. Okay, so we're looking into here. We look at the open circuit voltage. If we were looking into here, and we would say if we could break this circuit and still have things flowing, we would look into here and we'd say we can see Vs minus 0.6. So that's our open circuit voltage if we could measure that. Okay, this is a thought experiment. You know, you'd struggle to actually measure this. And then the short circuit current, if you short circuited that and said what's the current going through it, it's going to be IB and 1 plus and beta IB from the current source in here. So we've got 1 plus beta IB flowing through here as a short circuit current if we made this resistor to be 0. Okay, so that's what we got. We can make then a substitution back in then, and we can end up with because we know that IBs are going to be equal to VS06 minus 0.6 over RS, because we, that's just what happens when we look at what's going on in that loop there. And so the equivalent resistance then will be open circuit voltage over short circuit current, which if you put these two together, fortunately for us, these nasty coefficients will cancel out, and we end up with RS over 1 plus beta. So RS over 1 plus beta here, Vs minus 0.6 here is the Thevenin equivalent of looking at this if we were a signal. Now what does that mean? That means that if we're looking into here, we see a very small resistance. We see RS divided by 1 plus beta, and 1 plus beta is a big number. Yeah, 1 plus beta we know is beta, we know is a big number for a good transistor. So what we can see looking into here is a very, very small resistance. So we've made an impedance transformation from what's really here. Looking into here, we can now see a very small impedance, which means that if we connected something here, we wouldn't get much of a voltage drop, because if we consider putting another resistor in here, almost doesn't matter what the value of this resistor is here, because this one is so small. The voltage we see here, because of the potential divider equation, divides in the ratio of the two resistances. This is a small resistance, this is a bigger resistance, we have to say, means that this voltage here is going to be very close to this voltage here. So we avoid loading it. Okay, this factor of impedance transformation becomes very important when we consider loading, which means when we consider connecting other circuits to this and hoping that we get the same voltage out as we were expecting. We'll look at loading in a bit more detail. Right. So, in summary then, nearly the same input voltage, or nearly the same output voltage of here, just dropped by 0.6, so as long as Vs is quite big, this might be insignificant. So effectively we're getting the same, we can assume we're getting the same voltage out than we put in, just dropped by a small amount, but not multiplied by a small amount. That's important. And the impedance is reduced by 1 plus beta, so we've lowered the impedance of the circuit. So this becomes a very useful circuit for driving low impedances. If we have a small impedance here, we can drive it with this circuit, because this is likely to be even smaller, and therefore we don't get a voltage drop and we get the voltage out we expect. And it still has power gain, because we've got a current gain on the system. We've got IB going in and we've got 1 plus beta IB coming out, so we've gained the current. We haven't lost any voltage, and power is voltage times current, so the power gain must have gone up. All good. Right. The need for biasing. Right, so amplifying small signals. Amplifiers, as you're probably aware, are used for amplifying things, making things bigger. And we've seen with the two types that we've been looked at now, we've looked at a common emitter, we've looked at common collector, and the common emitter gave us a voltage gain and a bit of a current gain, so we had a nice power gain, and the common collector didn't give us much of a voltage gain, in fact didn't give us any voltage gain at all, but gave us a big current gain, so we get an amplification of power there as well. So we're getting the idea now, but how can we actually use this and how can we control this to do something useful for us? So here's our common emitter circuit, and this is its simplified transfer characteristic from V in to V out. So what we do here changes what comes out over here, and we can see that small inputs give us no change in output, and the output sits at a high voltage because there's no current flowing through here. As we increase the voltage, the transistor goes from off to on, and at this point it's very on, can't go on anymore, and we can't, and putting more drive into it makes no difference. It's doing the best it can at that point. And somewhere in between we've got this changeover, which we know is exponential, but we've modeled it with this sort of just approximate linear calculation. We want to amplify a small signal. We've already seen that we need to be in this region here to get voltage amplification, to get this mapping from the input to the output, and the more linear this is, the better the linearity of the output will be. But if we just apply a small signal straight into this system here, we're operating in this region, which means that we don't get anything out. So in a bit more detail then, here's our transfer characteristic, and here's our crude representation of an input signal that's small, and these are three possible points that might come in at. They obviously can come in at any point, but let's say that we put it straight in here. If we map it to the output characteristic, you can see that the output is never changing, so our output will look like that. It'll be a flat line at a high voltage. In the middle we've already seen, if we can manage to constrain this input signal onto this linear characteristic, we get the same thing but bigger in terms of voltage, and that's great. That's an amplifier. If we go too high, we operate in this region here, you can see we're operating in a position now where this bit will cause some amplification, so any signal going into this bit, the voltage curve, will result in a amplification factor. But if it goes beyond that onto this flat line, we don't get anything, so we get this sort of half amplification at that point, and if we go further up we'll just get nothing out. So we obviously need to make sure that our input signal is coming in so that it sees this part of the curve. Okay, and this is called bias. We have to bias our circuit so that any signals coming in are constrained to operate on this halfway house, this somewhere between on and off, which is not the natural operating state of a transistor, so we're going to do some work to get that happening. So this is called bias, but it's really an offset. We can see we're going to be offsetting from 0 to some point in the middle of this characteristic as our starting point. So we would like our circuit to be sitting in the middle of this operating characteristic when there is no input coming into the circuit. That's the best place to be. So the circuit is sitting there waiting for an input signal to come, and it's ready to amplify it, because we're going to, any input signal that comes is going to superimpose itself on top of this operating point and then just be able to move up and down this curve. Yeah, we don't want to be down here and we don't want to be up here. So we've got to add some kind a DC voltage to it somehow. We could add a DC source in series, but that's not going to be terribly practical, but you can have a go if you want. But there's a more useful technique. So this is where we're starting to add a bit more features into our circuit to make it a bit more practical. We start with our common emitter configuration. So we've got our load resistor up here, we're taking our output here, and before we had a resistor coming in here and our signal coming in there as well. So in this situation what we've done is we've split this input side into two. We've taken our input source resistance, and we've just connected it to the positive power supply. So that's just a fixed voltage, so there's going to be a fixed current coming down here now. And our input signal, the thing we want to amplify, we're bringing that into the same point, but we put a capacitor in the way now. And remember that capacitors don't allow DC signals to go through, but they do allow AC signals to go through. So we can now split this problem into two little problems and add the two solutions together, and that is a superposition problem. And we split it on the basis of frequency now. So we can say that there's one solution for low frequencies because of this capacitance. This capacitance will block out low frequencies and DC. And there's another solution for high frequencies because the capacitor becomes short circuit at high frequencies. So we've got two circuits to worry about. One is a low frequency circuit and one is a high frequency circuit, and overall the circuit performance will be the combination of those two. So, and more formally then, if we assume that our signal of interest is AC and is blocked by this capacitance down here, then when there's no signal coming in, we would just have this part of the circuit to worry about. This is called our DC solution. So we're saying there's no signal coming in, it's been blocked. What does the circuit look like, or what is the operating position of this circuit when there is no signal coming in here? And we can look at this and we can say, well, there's going to be a current going down here, IB, and that's going to go through the transistor, and that's going to cause IC to flow, and when IC is flowing, we're going to end up with a voltage at this point here. The question is, what is that voltage, and how do we make it be what we want it to be? So we can do a quick analysis on this. So you can start to see that we're implicitly applying all the sort of linear theory we learned now without formalizing it. We can say that IB is just equal to VCC, which is this voltage here, take away VBE, which is this voltage here. So it's just the voltage drop across this resistor because there's nothing else in this path, and divide that by RB because that's the only resistance we've got there, and that defines what IB is into this transistor. We don't know what VB is, to be fair, at the moment, but that's the equation that describes what's going on there. We also know that IC equals beta IB, so the current through here is going to be beta IB, and that depends on what IB actually is, but now we've got an equation for IB. And V out, the thing we're interested in, we know is just VCC minus the voltage drop across here. That's the quickest way to get to that. So that's VCC, take away the voltage drop, which is going to be IC over RL, and we know that IC is defined by beta IB, and we know how to define beta. So we've got it all. So by adjusting RB, changing the value of this, we can change IB, and that allows us to control the output voltage. And if we get that right, we can position this transistor in the active region, so halfway up that curve, for no input signal. Okay, now if we think about this, what we've done is we've positioned ourselves somewhere on this input curve. This is what's called our operating point. And with no input signal, all we're going to be doing is sitting at this point here. So if you wanted to analyze that by load lines, you've got a load line for the input diode of this circuit here, and you've got a load line that's defined by RB. And of course all of you will have had a go at the examples on the ECS notes page for drawing load lines, so you'll all be familiar with this now. You draw your load line on, and that will tell you if you wanted to know exactly where your operating point actually is. So it's going to be sitting there, and any new signal coming from V in, okay, which is AC, that passes through this capacitor, is just going to add itself to the signal at this point and move up and down the exponential a small amount. And the smaller it is, the closer we can approximate it to a straight line. Right, that's the fundamentals of biasing. The small signal model, remember we've done a large signal model, we now look at a small signal model which will tell us exactly what's going on at that point there. So the DC just moves the input signal up and down. The DC moves the bias point up and down, the operating point, yes. It's, yeah, okay, so if that's clear, that's fine. So, what is a small signal model? In words, a small signal model is a linearized model of a non-linear system. And so we're starting to recognize this as being a good thing. We've linearized it, we've taken away all the complexity, but it started off being non-linear. And we center that around an operating point. And an operating point is the bit where the linearized part is exactly the solution to the non-linear part. It's only accurate at one point on the curve. The accuracy elsewhere is dependent on how non-linear the curve is. So usually we are limited to small excursions, small changes from this operating point, because it starts to become non-linear quite quickly away from that. Hence small signals. So we have to deal with small signals. So this is why it's linear. So we're allowed to linearize things for small signals because the error is small. Once you start putting big signals in, the error gets bigger. Right, the derivation of a small signal model. We split VBE. So VBE is this bit down here, which is the bit that's controlling the current going through the transistor. We're going to split that into the two parts. The bias term, which is the DC solution, so remember we're ignoring this, so that's basically the same calculation we've just done many times. And then the small signal part, which is the bit that's coming in when we apply a signal. So the total voltage at this point here is the combination of the DC solution, which shouldn't move once we've calculated it, and the AC solution, which is going to move up and down a bit. Okay, so VBE, so this is where we have our problems in describing it. Little v, big BE means the total, the combination of small and large signal, and that is the combination of large signal with a capital V and a capital BE, and the small signal, which is a little v and a little BE. Okay, so that's, just remember we're dealing with two parts of the signal here. We've got a static part that's not moving and a bit that can move, and the bit that moves comes in through here, and the bit that doesn't move comes from down here. And we can define the same kind of double variable, if you like, for all currents and voltages in this circuit. It's just the addition of the static solution, the DC solution, and the AC solution. So it's a superposition problem. So what we're looking for a linearized model of our transistor that will easily allow us to calculate the gain of our amplifier for small signals when the transistor is already biased. So what we're really saying is, what is the actual gain of our circuit, given that we know what the circuit actually looks like, but we're not actually sure about what's going on in the transistor. So we've already used our large signal model to get an idea of the biasing conditions. So that gives us the bias conditions at one point, and that's all we need for biasing, because that's the DC solution, it's never going to move. So we can apply our simplified large signal model to get that condition. Right, and then we need to use that biasing point to calculate the actual gain, the accurate gain of the transistor amplifier for those small signals that we add on to that. And that's where we're going with this. So I think a good point is to stop now, because if you've been concentrating, you all have been a bit worn out by that. And we will pick this up again whenever we next meet later in the week, and understand how to develop a small signal model. And once we've done that, you'll be pleased to know that we're then armed with enough information to analyze any transistor circuit in a nice linear fashion. And so we just have a simple set of rules to apply then. But we've just got to get over this little hump of getting our small signal model out before we can do that. Okay, so we stop at that point, and I'll see you probably tomorrow, I think it is.